properly. Okay, so OpenGL is just a software interface to graphic hardware adapters. Can be used to program your own graphic adapter. It's called open because it's standard, can be freely accessed by manufacturer. The API that OpenGL provides you are not programming language like C or C++. Instead, you can use those API for calling some function that allow to define some models that you want to visualize, use textures or colors over them, and perform some kind of operations, like for example the projections, in order to see some model 3D. And the main output of all the process is to render, so to visualize on a two-dimensional surface, the one of your monitor, all the models you plan to visualize, to use for any purpose you may have in mind. We choose OpenGL and not its direct competitor DirectX just because OpenGL is available for a wider range of devices, while if you use DirectX you usually are somehow linked to anything that is window based, a PC, a phone, tablets, Xbox, etc. But keep in mind that the basic concepts are more or less the same. There is no such a big difference between OpenGL and DirectX, aside from specific syntax or the way you code, basically. But the concepts are exactly the same. There is this OpenGL specification, which is kept by the organization that keep OpenGL under control, which can be implemented as a library by the specific hardware vendor. If I produce an NVIDIA card, for example, I take those specifications and I implement on my card in order to allow any user to use the same function, the same commands, and obtain the same effect on my hardware exactly as it would have been on another hardware. This makes OpenGL indeed portable. So, if you have some software drivers that allow you to connect a machine, a device, with a graphic adapter, then you have a specific OpenGL implementation. Another way for explain this is that it doesn't mind how your hardware performs some function. What is important is that if I call a function using the standard of OpenGL, I expect to obtain the same results on any graphic adapter, independently on how it was implemented by the manufacturer. It is also possible to have some implementation of OpenGL which doesn't require a specific hardware, but instead moves the majority of operations that are usually performed over the graphic adapter hardware over the CPU. Of course, this reduces the performances, but there are libraries, for example Mesa 3D, that allow you to use OpenGL without having a graphic adapter enabled for using OpenGL. Maybe because it's very old. Nowadays, that's not really any longer an issue, but let's say up to 5 years ago, there were graphic adapters which doesn't support all the full set of features of OpenGL. So using a software implementation can also be useful. And software implementation are useful also in case you have, for example, a virtualized a virtual machine and you want to use some sort of graphic acceleration inside your virtual machine. Not all graphic cards allow you to virtualize the graphic cards, so that was a way, a workaround for that issue. Okay, OpenGL is basically implemented as a client-server system, meaning that there is a client-side part of the application, code that is run by the CPU of your machine on the main memory, and a server-side part of the application, which is run directly over your graphic adapter hardware and resides on its memory, on that part of the memory. The client sends some OpenGL commands, and of course, those commands are executed by the server-side part of the application. The client-side part of the application can be written using any language that you prefer. In case of WebGL, we are going to use JavaScript, but if you want to use a standard version of OpenGL, not WebGL, you can use from C#, C++, Basic C, any kind of language can be a client-side language, while the server-side uses only one kind of language, which is the GLSL, graphic library shader languages. That's it. And we are going to use that program, and all the part that is asked you in this course at the exam is going to be exactly and specifically only on the GLSL part, because we consider that you are able to program in any kind of language, be it Java, JavaScript, C, C#, etc. We want to teach you how to program your graphic card. This connection between the client side and the server side of an application can also sometimes, in some implementation, can also work through a network, but just for you to know. OpenGL then employs state model or a state machine to keep track. It works like a state machine basically, and keeps tracks of all the variables connected somehow to its function, etc. This avoids the passing of too many arguments on each function call, which is pretty important for performances issues. And this means too that once set, a specific state remains until some other function changes that state. This is an example. This function GL enable and of course GL disable. There is an enumeration of capabilities that are exposed. For example, in this case, the activation or deactivation of the Z buffer, meaning that there is a specific buffer who controls which object in a 3D world stands behind another object, because I want to see only the closer to me of a list, not all of them. I enable, for example, this function. Also, another functionality which is not on by default is the transparency. If I want to enable the alpha channel or not, I state with a GL enable that I want it on or off. It depends. Just a slide about its history. It's pretty okay, not so much, but quite recent. It depends your birth date, but okay, for me it's quite recent. It was created in 1992 in Silicon Valley, and of course its purpose was the visualization of 3D contents. Up to 2004, the evolution of graphic adapter doesn't allow to visualize things in so many different ways. But as technology evolved, a greater flexibility was required by the programmer in order to do things more complicated than before that date. So new functionalities were added to OpenGL, and it was in this date that the version 2.0 of OpenGL introduced this OpenGL shading language. In this case, we face a very C-like program which is used to perform rendering operation. Since it is very important for this course, we will address this topic in a future lesson, in many future lessons, in order to analyze in depth. After the introduction of this GLSL, many different versions of OpenGL started to spawn. Two of the most important were OpenGL ES, which stands Embedded Subsystem in 2007, and was a version of OpenGL to be used only with embedded devices, which are by default supposed to have less resources available to them, and WebGL in 2011. In this case, we can access the functionalities of OpenGL within web browsers using mainly JavaScript. OpenGL can be considered as a subset of all the functions that are available to the standard version. And this is because, for example, many functions that found no use basically on an embedded system were stripped down. For example, it is very unlikely that on a standard mobile, I don't speak about the latest one, but let's say also those of a couple of days ago, you don't have to render very complex polygonal objects. So you don't have to specify objects in terms of very complicated sets of vertices. So we will see this into details in a couple of lessons. But since any 3D object is basically a collection of triangles, the functionality of OpenGL is to draw on your screen triangles basically. But if your modeling tool, let's say Maya, 3D Max, allows you to model with NURBS very complex surfaces, function, etc., you may find yourself at the end with objects very complicated, with faces not triangular, but made by many vertices. OpenGL then tried to simplify, to transform, let's say, a quad, that is a face with 4 points, into 2 triangles. This is avoided at the software design time when using embedded subsystem, which usually don't have to deal with such a complicated feature, and so such functions were stripped out from the specifications. Another thing which is peculiar about OpenGL ES was the fact that you have all the interface required for managing Windows. Since OpenGL wants to be the more cross-platform as possible, it doesn't care about how you create the portion of screen on which you put everything you draw. Usually this is up to you and other libraries that you use in your client code. But OpenGL allows you to do that, also because the particular situation about operating system and things like that in an embedded device. This is just a detail, but we don't care about it. Let's go to WebGL, which we are more interested in. WebGL 2 utilized the OpenGL ES 2.0 specification. That's why we introduced the OpenGL ES. Works in all modern browsers. I tested it on Edge this morning. It seems to work. I'm not sure, but it seems to work. Also in Explorer. Explorer allowed the use of WebGL only in the latest release. Before it was quite tricky to use with it. But to avoid all those problems, we will use Google Chrome, which works perfectly fine for this. And we solve the problem like this. I introduced briefly the fact that we need a portion of the screen on which we can draw. This portion of the screen, this object, is called in many ways, and it depends really which is the program, the library, which allow you to have such portion of screen. Since we are going to use HTML5, we will exploit the capabilities of the canvas element to draw on it. While the OpenGL WebGL functionality will be accessed using JavaScript. So basically all we need is Google Chrome and a text editor, and if your hardware supports WebGL, which should be the case, we can draw even complex objects. Okay, windowing. Windowing was a very tricky part of the course up to 2 years ago, because we started this course using C, basic C, for programming the client part. And even if on Ubuntu, any other Unix-like, on Mac, iOS, on Windows, you can program in C, all the problems, so that the course becomes some problem solving by our part of all the specific problems that arise, was due to the fact that different operating systems have very different ways of managing the windowing and the screen that you can see. So you are going to require very different libraries depending on the operating system that you have in order to see something, which creates at least 3 versions of the course, apart for doing things on Mac, apart for doing things with Ubuntu, and another for Windows. That's why we switched to WebGL, which has exactly the same capabilities for what we intend to use, but less problem. And other things that we don't have 2 things. So on WebGL, we cannot handle any kind of user input, and we cannot perform any windowing task. OpenGL usually relies on the operating system for managing both of them. As you can see, there are many different, just example, there are more than that, but you see, there are many windowing systems. Also on Linux, you can decide which one you want to use, so that creates a lot of problems. Why? Because all of them expose a different set of APIs. Then you have the necessity of more libraries. There are some listed there, GLFW, Glue, Glut, etc. But there is plenty of them. And you know that when you install a library, everything can go very bad sometimes, if you are not lucky. Instead, WebGL is more lucky because it can take advantage of anything a web browser can do. Register the key pressure, events connected to the mouse, etc. And of course, the windowing. So, let's see something about the canvas element provided by the HTML5 in order to see what we can do with it. Okay, on the canvas element, you can by scripting, you can draw things on your web browser page. This is what the important part is this one. It provides you with a frame buffer. The frame buffer is what you try to create by using libraries, by interfacing with your operating system, because you need a portion of the screen, which is also a portion on memory, and inside that portion of memory you draw your picture, what you want to draw. Then this part of memory is moved when the monitors send a sync signal, is moved and visualized. Is the part of memory where you build pixel by pixel in many different ways the final image before it is displayed. So you need a frame buffer, a region on which to put any element you want to draw, any color, any element. The canvas element support different API. You can interact with this element through many different ways. We will see the main two, the standard and the WebGL one. Has some properties like width, height, and ID, which is useful because we can then assess methods and perform operation on that, and the area in the canvas can be manipulated using the JavaScript, and that's why we will use JavaScript. This is a snippet of code. You see the canvas element is called by the tag canvas, and there are some properties, the ID, which is very important. Inside the opening and the closing tag, you can write anything, and it works exactly like when you put an image in a web page. If the image is not displayed, in this case, if the canvas is not open, the text message you put between the two tags is displayed. Otherwise, it is covered, and it is a simple debugging trick. Okay, after we obtain the canvas object, we have to create the context. The context is a data structure, basically, which keeps tracks of everything, all the operations, all the variables we set that we want to use inside that part of memory. There is a list of some examples of state values. They are independent, which means that one doesn't affect directly another one. The state of one does not affect the state of another one, but of course together they change the global state. So information about the current path, which kind of filling of this path, colors, if we are using an alpha or not, if we want to use and enable the anti-aliasing. I don't know if you already seen something about anti-aliasing. Basically means that if you don't want to have jagged edge for non-linear shapes, you have to do something in order to smooth the border and see a nice smoothing, let's say, circle instead of something that is blocky, shadows, etc., etc. Okay. A context is pretty simple to be requested. There is a function which easily you can call on the canvas element, get context. You will have an ID, but more importantly is the list of arguments that you can pass to the get context. The get context is a function which is currently under development. So we will see two kind of context, the 2D one, just for drawing in the basic way over the canvas, and the WebGL. If you want to use WebGL using Edge or Explorer, you have to use instead the tag experimental WebGL. It's not experimental at all because it's pretty final as a context, but they keep for Microsoft is obsessed with retrocompatibility. So since at the beginning experimental WebGL was the way for calling this kind of context, they stick to this definition, and they are the only one that use this one. If you use WebGL, you are not able to create the context in Explorer. Okay, at this point we get, as the return of the function getContext, we have an object that exposes all the function about WebGL that we need for drawing. Not only on WebGL, all the function, the API that we want to use for drawing. And this is the snippet of code. I put the tag script just to show you that is JavaScript, is not, of course, HTML. The first one is the canvas. You get an element from the document. The document is the root of what you are doing. And my canvas is an arbitrary name that you can give to the canvas object. And then you create the context by calling the getContext over the canvas object. Now we have the frame buffer, which is the portion of the screen on which we can drive. We have a context, a data structure for keeping track of everything we want to draw, all the properties of what we are going to draw. So we are ready to begin drawing. So now we have to specify the data of our figure, of our pictures, the shapes we intend to draw. The most common way for doing this in a scripting way is by the use of geometric primitives. In the basic 2D context, we just have two basically, rectangles and path. Path can be lines or circles. With rectangles, you draw a rectangle. With a path, you move the cursor around the screen and you decide if, while moving, it also has to draw or not. The command rectangle, which requires a position in the Cartesian space, an x and a y position, and the width and the height of the rectangle. Of course, draw a rectangle that must be stroked or filled later. Fill rectangle, of course, fill with the last color that you set. Stroke just creates an empty rectangle. Path instead are used to draw lines or more complex shapes, for example curves. You need to begin a path somewhere or state that anything clear the state variable associated up to that point with the path. Begin, move the cursor to a specific point. If you want to move but also to draw the line, you use line tool. If you want to close, the last point that you use will be automatically connected with the first one. And if instead you use the arc, you are going to draw a curve that, if closed, becomes a circle. We will see some function that is also able to draw circles without using arc, or we will see how the arc function works, said in another way. Okay. Before starting to see something practically, I have to spend some word on something that you probably already have seen in the theoretical part, but something about the coordinates of the drawing space. If this is your screen, which have the origin in the topmost leftmost corner, the canvas is a subset of all this portion of space, which works at the same axis orientation of the monitor. We will see that with the WebGL things are different. So when you want to draw something, you have to keep in mind that the coordinates are those. The values also are quite important. When you work on a canvas, you work on using pixels as a measure unit. And the values that you use over the canvas must be mapped over the screen in order to they must be transformed, because you are operating just in a portion of it. This kind of operation is usually transparent to the user and performed directly by the browser. So, for example, a point at the center of the canvas, a canvas that has, let's say, 800 for 400. If you put a point in that position, the position in screen coordinate will be very different. The mapping from one to the other coordinate set, as I said, is you don't have to care about that. The solution, of course, allows that independently from the specific shape and size of the hardware you are using, more or less things looks the same across different solution. One last thing which can be of some interest. The monitor's pixels are usually squared. The whole number coordinates usually indicates the edge of those squares, as you can see from the picture. So if you want to draw a line which is, let's say, 1 unit wide, and you use whole numbers, in this case I'm creating a line starting from 1, 0 to 1, 3. This is the line I want to draw. It will be interpreted like this, because you cannot lit just half a pixel on your monitor. So automatically you're going to get a line which is 2 pixels wide. On the other hand, if I use, let's say, 1.5 as my x value, then I will lit just 1 pixel wide line. Okay, about the anti-aliasing, I showed you. This is one of the figures we are going to see. Okay, this is the difference. If you use anti-aliasing, there are specific algorithms that change a little bit the color of the pixels in order to smooth the line. Otherwise, without anti-aliasing, the other one is the line you get.